Much. Hi, my name is Caterina. I'm doing my PhD at University of Padova, and I'm going to talk today about the gamma ray follow-up or GFU platform for IceCube, which is a tool for real-time studying of the external events. And also Elena is working with me on this, some of the students sitting there. Hi, Elena. So, okay, now it's much easier for me to explain the motivation for this, thanks to this morning lecture and also for Catherine's talk. As we have heard, it is the time-integrated search for neutrino sources has failed so far, and the key point is that what we try a different approach, that is the identification in real time of transient sources of neutrinos, with the aim of sending low latency alerts to the astrophysical community, and in particular Cherenkov telescopes, to encourage multi-messenger observation. And so, in a nutshell, the gamma ray follow-up platform has the aim of selecting good neutrino candidates for this program. And we start from the processing and filtering at the South Pole, where the GFU filter selects through-going muon tracks, and this reduces the rate down to 6.5 millihertz. And the filtered data is sent to the Madison computers, the IceCube Madison computers, where the real-time analysis is done in basically two ways. One way is the selection of single high-energy neutrinos, and the other way is the search for neutrino clusters, either by the monitoring of predefined sources or searching for neutrino flares in the whole sky. And in this way, when some very good candidate is found, private or public alerts are generated and sent to the astrophysical community. So just to go a little bit in details, the high energy single event search is motivated because, as we say this morning, high energy means a high probability of having astrophysical origin. But this has the cost of performing very aggressive cuts in energy. And in this way, we are mostly sensitive to the region around the horizon. And as a response to this analysis, public alerts are sent, which are called bronze or gold, depending on the astrophysical probability. The other approach, my favorite one, is the search for neutrino cluster. This is done with ambient maximum likelihood method, and it allows just to do loser cuts, that is looking for clusters. We pick up also those low energy events that are buried under the background or at low energy. So in this way, we are sensitive to lower energy and uniformly to the whole sky. And at the moment, the alerts are private, and they are sent for the monitoring of catalog gamma ray sources and for the search of flare in the whole sky. Okay, so the maximum likelihood methods works like this. So we build the likelihood for a set of an observed event by assigning a signal and a background probability to each event. And this is done with comparison to probability density function from a spatial part, that is that tests the compatibility with source location, and the energy probability density function that exploit different spectral index for either background or signal, and then also a time PDF, because we search for a time window where neutrinos arrives in time correlation. So in the end, so we build the likelihood, we define the test statistics, and in the end, the fit parameters that we change to get the best test statistics are the number of signal events and the spectral index, and of course the time window that we are testing. So the time scan algorithm works like this. We have an event that arrived, that we observe a neutrino in IceCube with a signal over background probability larger than 1, and this triggers the time cluster analysis. And so the likelihood analysis is performed going back in time, testing the likelihood for all possible event combinations of what has come before. And this is done up to a maximum time window, of course, of 180 days. And for each trigger, the result is the best statistic. So the time window and the NS and the spectral index that gave the best statistics. And whenever the significance crosses a certain threshold, an alert is sent to partner telescopes. So looking for results in the archive that we found in the archival data that were collected by IceCube from 2011 and 2019. We say that for the test of a predefined list of gamma ray sources. We are testing 339 sources that are monitored by the partner telescopes that are MAGIC, Veritas, and HESS that we already saw this morning. And the most significant flare was recorded in 2015 coming from this blazar. And it was a flare of neutrino that lasted about 7 hours, and the post-trial significance that is corrected for trial factors was of about 2 sigma. And there was no there was nothing relevant reported by Fermi in coincidence with this event, so this is not conclusive yet. And regarding instead the unbiased all sky search, in this now we don't test a particular source position for the likelihood, but we take every incoming event as a testing hypothesis. And so we found that the hottest spot is found at this position, and the cluster was recording in about 10 days, and the post-trial significance in this case is even lower. And this is because when we test the whole sky, we do a lot of trials, and so we have strong corrections for that significance. And even in this case, we have no conclusion, no conclusive correlation with Fermi activity, with Fermi analysis. So what is happening after 2019? After 2019, the alerts are being sent as the state of the art. And we have sent so far about 76 single track alerts and 55 alerts for neutrino multiplets to the partner Cherenkov telescopes. And the Cherenkov telescopes have their own follow-up programs as a response to the alerts that IceCube send. And in particular, the aim is to search for the very high energy counterparts and to check for any change in the status of the emissions of these sources. And it is up to the telescopes if they want to observe or not, depending on the neutrino event itself, but also on the weather conditions and observation constraints. And but in general, within a few days, they start to observe at the point in the sky where we say that the neutrino is coming. And sometimes, like for gold alerts, they also have automatic repointing setup. So to conclude, so far, the real-time alerts and the follow-up of partners telecom did not bring any conclusive result, but we are going on. So we hope that someday we'll find something interesting. And the offline search for the flare significance evolution did not find any access above background, but stay tuned because we are going soon to deliver some new results. And what are future perspectives and what I am working on is the improvement of the event selection and reconstruction and the algorithm efficiency, and also to set up a self-follow-up of the significance evolution after an alert is sent, because at the moment we can only do this offline, as I show you in the archival data results. And also we are working for extending the source list that at the moment is a lot biased by the fact that the partner telescopes are the Cherenkov telescopes, so this put a lot of bias in the selection of the source that are monitored. But in this perspective, we also would like to make these alerts public because the more the merrier, and we extend the community to look for these multi-messenger events, it would be much better. So this is all. Thank you.
Questions?
The unbinned analysis that you were talking about, where you tried with the source catalog and without it and didn't find anything with significance, with that search, did you also have that aggressive energy cut implemented as well?
For the flare search?
Yeah.
Well, the first cut is on the event that triggers the analysis.
Oh, okay.
But however, combining a space and energy PDF let us be less strict in the cuts in energy, and
okay.
also the scanning back in time and selecting previous events in time correlations allow to pick also events that would not have passed the filter for high energy single events. So in this sense, we have looser cuts in energy.
Okay. Cool. And I guess my follow-up question is, you didn't mention that you detected the TXS flaring in that analysis?
Yeah, it was when the TXS was observed, this particular setup was not there.
Oh,
And
okay.
however, what we have seen, and also the TXS was not in the list of the monitored sources for the flare search, because when I said here that we are very biased by the Cherenkov telescope, one of the criteria for the selection of the sources is a well-known redshift, and we didn't know the redshift of the TXS before the TXS 2017 event. So now it is a monitored source.
Okay.
And if we look into archival data, that source with this analysis setup would have triggered 2 alerts prior to 2017. So this is also, in my opinion, a motivation for this approach, because yes, it recognized TXS as an interesting source.
All right, thank you.
You're welcome.
All right, I think let's move on to the next speaker. Thank you.
And yeah, the last speaker is Vittoria.
Microphone.